Okay, so we are going to use today's lecture to kind of continue digging into the periodic table. We're going to be talking about electronic structure and atomic structure of an atom, atomic structure, and then we're going to talk about the different subatomic particles, the kind of building blocks or components of an atom. So, for a very long time, there was not really much knowledge about what an atom looked like. I mean, as soon as there was a theory that everything was made up of atoms, then people started to wonder, like, okay, well, we've got these building blocks that make all matter, but what are those building blocks made up of? Sure, this is the simplest possible thing, but is there something simpler? And so we see this progression on this slide from the left to the right, that basically in its earliest idea or its earliest incarnation, the idea of what an atom was it was one ball. And there were lots of these balls that would be put together to make matter. Then this spot in the middle, this model that's in the middle was a model that was proposed in the mid-1800s. And the idea of this model was that there are both positively charged and negatively charged components of an atom, and that the negatively charged components of an atom and the positively charged components were kind of making this mass together, like they were randomly distributed. And this was referred to as the plum pudding model of an atom. And so the idea was that, and I'm not sure exactly, maybe you could replace plum pudding with like a cobbler or something like that. But the idea was that all of these negative charges were randomly distributed. They were like the pieces of plum in the plum pudding. So you would, go towards this atom and, rip out one part of it, and you get partial negative or partially positive charge portions. And ultimately, there are some experiments that were done that basically dismissed that idea and gave us this idea that's shown over to the far right here, which is the most modern model of an atom. And the most modern model of an atom is that basically your electrons are randomly distributed. Maybe not completely randomly, but they make up this electron cloud. And at the center of this electron cloud is a part of your atom known as a nucleus. That nucleus has two components, neutrons and protons. So your neutrons and protons are packed into the exact center of this electron cloud, and they make up this nucleus. Now, I bring this up because this is in contrast to our plum pudding model, our model that's shown in the middle. If you look at that plum pudding model, we have this positive charge that basically encompasses this entire kind of sphere or ring, rather than it being localized in the center. So the biggest difference was that your positive charges, your positively charged subatomic particles, whenever I say subatomic, I mean, well, smaller than an atom. So those positively charged particles in the modern model of an atom are at the exact center. I kind of think about it as an atom is almost like a sphere, like the Earth. And the nucleus is that liquid hot magma core at the center of the Earth. So in the nucleus, you've got positively charged protons and uncharged neutrons. So we have the plum pudding model, which was dismissed because, well, there's a concentration of positive charges in the exact center. So this positive charges randomly distributed is inaccurate for that reason. So here's another look at this plum pudding model. And essentially what was done here was a fellow by the name of Ernest Rutherford at I believe it was McGill University in Montreal, Quebec. His experiment was, his experiment to disprove his experiment that disproved the plum pudding model was that he said, listen, if let me go ahead and let me use this. What he did was he said, all right, well, here's an atom. And we've got a couple of different options. If this atom has positive charges distributed throughout the atom, so if that plum pudding model theory is correct, then when I shoot something with a positive charge at this atom, think about a magnet as when you have two of the same poles of a magnet, the north and north poles of a magnet, what are they going to do to one another when you bring them close? They're going to repel. And what's going to happen is you're going to take your north end, bring it to your north end, and then one of the magnets is going to do a quick spin because it wants to attract the opposite. So using that same sort of principle, Ernest Rutherford said, if I shoot positively charged particles at an atom, here being my atom that's really poorly drawn there, and these positively charged particles are everywhere, well, then what I would expect to see is that the positively charged particles that I shoot at this atom go off in all these crazy different directions because they would hit something. They would hit a positive charge and repel from it. Does that make sense? Okay. Then, so this is his theory shown here on the right. And then he was like, if, however, the positive charges were all localized in the center of an atom, and then I shoot positively charged particles at this atom, then some of these positively charged particles, they're not going to hit anything. So what are they going to do? They're going to go straight through. Does that make sense? So his theory was, we've got the plum pudding model where there's positive charges everywhere. And then another theory where there are only positive charges in one specific location. If the plum pudding model is true, then I'm going to see all these ricochets, basically, of these positive charges. If that's untrue, then you could think about it almost as the number of ricochets that I see is going to be considerably lower. Because, I mean, if we look at this, 1, 2, and 3, these 3 charged particles, what's going to happen to 2 of them? Well, 2 of them go straight through because they don't collide with anything. So I'm going to label this the PP, or the plum pudding model, and then I'll call this the central. I'll just call it CNTRAL. Central being where that proton is, or that the nucleus is. And ultimately what Rutherford saw was that when he shot positively charged particles at atoms, the number of ricochets was fairly low because many of these positively charged particles were basically going straight through the atoms because they didn't hit the nucleus. Some of them did, in which case you'd see these deflections, but most of them you did not. So that's essentially what he was doing. That's the experiment that he designed in order to do this. Now, what I want you to take away from that is that Rutherford disproved the plum pudding model. Rutherford then, or his experiments, supported a nucleus as being where positively charged subatomic particles were or are. Now, of our 3 subatomic particles, these are the 3 that we need to know about. They are protons, neutrons, and electrons. They have different locations. Protons and neutrons are in the middle, found in what is known as the nucleus. The electrons are outside of the nucleus. The electrons are kind of like, they're just moving around. They're in constant motion. And whenever I think about protons and neutrons and electrons. Electrons are, they're going to have different masses. Your protons and neutrons have a mass of what is known as one atomic mass unit. So 1 AMU. And that you have that tilde 1 AMU because it's roughly 1. It's 1.000 and on 30 decimal places. The charges of our different subatomic particles. Protons have a +1 or a positive charge. Neutrons have no charge whatsoever, and electrons have a negative charge. Protons and electrons have opposite charges of one another. Now, that to me makes understanding this model or our nuclear model of an atom a little bit complicated. Because if you've got positively charged protons in the center of the atom, and then you've got electrons floating around, wouldn't those electrons gravitate towards that nucleus because they're opposite charges? And the answer is yes, they would. But keep in mind, in any given atom, you don't have just one electron. You have, let's say that you have 2 or 3 electrons. What are all of those electrons going to do to one another? They're all going to repel other electrons. So just as one electron says, I'm going to the nucleus, well, then the other two say, by hell or high water you are, I'm going to the nucleus. And then when they get closer to the nucleus, they're going to be kind of pushing one another off. So pushing one another away. So there are a couple of things that you need to know about your subatomic particles. When we were looking at the periodic table the other day, we looked at our whole number. The whole number on the periodic table is what's known as your atomic number. That happens to be the same number of protons that an atom of a given element has. For example, if I had one single atom of francium, if I was able to capture one atom of francium, francium has an atomic number of 87. That tells me that in the nucleus of one atom of francium, there are 87 protons. So 87 positive charges make up that nucleus. In addition to that, if we again use francium, Fr, we got 87, and then 223. What those numbers also tell us is that we can deduce the number of neutrons that one single atom of francium has. And we can deduce that by saying the number of neutrons in the nucleus of francium is our mass number, in this case 223, minus our number of protons, 87. So if we did 87 minus 2, or 223 minus 87, that would be, let's see, 223 minus 87. You know what I'm going to do? I'm going to figure out myself, because I have my drawing tablet and I have a bunch of junk. But I'm going to see if this works. The last time I tried it, it was very not functional. We'll see. Well, it's not a good start. Let's see about this USB. Well, maybe. Nope. When we're on Zoom, this is what I'll be using mostly. So we won't have to watch me clumsily draw with the mouse. No dice, everyone. Okay, so 223 minus 87. Let's see. Boop. 1, 1. We got 6. 1, 1. 11 minus 8 is 3. So we just learned that one atom of francium, the nucleus consists of 87 protons and 136 neutrons. So if you look at the periodic table, the number of protons and neutrons are numbers that you can extract from that very easily. In addition to that, our number of electrons, if a term like the elemental form or an atom of is used, then you have an equal number of protons and electrons. So that term there, neutral atoms. Well, what does neutral mean when you're talking about positive or negative? Well, it means the number of positive charges and negative charges are equal to one another. They cancel one another out effectively. So if I said a neutral atom of cesium, Cs, has 55 protons, how many electrons does a neutral atom of cesium have? 55. Now, where it gets a little bit hairier is if I say, hey, you have an atom of cesium, but it has a charge of +1. Well, that means that first and foremost, it's not neutral. That means that the number of protons and electrons, therefore, are not equal to one another. The number of protons is greater than the number of electrons. We're going to get into that more a little bit later, but for the time being, this right here tells you almost everything that you need to understand or to know the subatomic particles of a given atom and to be able to deduce how many of each subatomic particle is present in any given atom. So, yep. Now, as a sort of question here that you might see on an exam or something like that, which statement is true? The nucleus of an atom contains neutrons and electrons. No. How could we correct that to make that a true statement? Well, replace electrons with protons. The atomic number of an element is the number of protons in one atom. Yeah, sounds good. Let's look at the other two. The mass number of an atom is the number of protons in the nucleus plus the number of electrons outside. Nope. Because it's the number of protons plus neutrons. D, the number of electrons outside the nucleus is the same as the number of neutrons in the nucleus. That's also incorrect because it's the same number of protons in the nucleus. Now, with all that said, I want you to try to think about our nucleus in a couple of different ways. Basically, all of the mass of an atom, we look at this right here, all of the mass of an atom is packed into that nucleus. The electron cloud surrounding that doesn't really carry much mass because the mass of an electron is considered to be almost negligible. What's the charge of a nucleus? Well, if you get rid of all of the electrons, then it's going to be positively charged. The electrons are not there to cancel it out. Now, we talked about these a little bit the other day. Isotopes. Isotopes are kind of different variations of an atom. Isotopes are atoms with the same number of protons, but different numbers of neutrons. Here what we have is an atom. On the far left, we have an atom with a single proton. So one proton is an atom with an atomic number of 1. Now, if we look at the model in the middle, our nucleus consists of two things. One of them is a proton, and the other is a neutron. Is this still a hydrogen atom? It is, because the number of protons has not changed. And if you look at this model on the far right, how many protons are present there? Just 1. So it is still a hydrogen atom. These are, however, 3 different hydrogen atoms. Same number of protons, but different number of neutrons. This one on the far left is a hydrogen atom with no neutrons. The one in the middle is a hydrogen atom with 1 neutron. And then the one on the far right is a hydrogen atom with 2 neutrons. So the differences between these are ultimately going to be, we'll dash back for a second. We can calculate the number of neutrons by looking at our mass number and subtracting the number of protons. Or heck, you could look at this as you can calculate your mass number by adding up the protons and neutrons. Here what we see are different isotopes of hydrogen. Hydrogen 1, 2, and 3. These mass numbers differ because the number of neutrons differ. This one in the middle is one known as deuterium, and then one on the far right is a hydrogen isotope known as tritium. These are used for a number of different purposes. I think that tritium is mentioned in, I think it's Spider-Man 3 with Octavio Octavius Octopus guy. I think tritium was what they were like, yes, tritium made him an octopus. I don't really think that that's how that works, but you know, I've never tried it, so I can't tell you for sure. I tried to say sure and certain in the same word. So these are different isotopes. You know that they are all hydrogen because the number of protons is the exact same. Everyone follow that? Great. You can build an atom with this exercise that will be linked, or that's linked on the PowerPoint as well as on the PDF. And essentially, you can, the way I think that this is helpful, or I like to visualize this because it helps me understand, it helps me track, like, what do I have going on there? So what does my nucleus consist of? Well, if I have a nucleus that has 13 protons, I know kind of the building blocks that I have to use. 13 protons is the atomic number. 13 is an atom of aluminum. So if I've added 13 protons to my nucleus, what else do I need to add to my nucleus? Well, my mass number is 27, so I have to add 14 neutrons. If I wanted to, so whenever I always like to think about that as I've added my protons, I've added my neutrons. What's my charge? Well, before I get to that, I have to reflect and say, have I added any electrons? I have not. So what's my charge? It's plus 13. Then as I add 1 electron, now it's plus 12, another electron, plus 11. And my charge is going from an extremely positive to a lower positive because electrons have a negative charge. Oh, okay. So this is a nice atomic symbol that you can use to look at all of the information that we've so far looked at, our mass number, our atomic number, our symbol, but what this is adding in is the charge. Our charge of a given atom is the number of protons minus the number of electrons. If it's not shown, it's going to have a charge of 0. So if you ever see Na plus, well then you probably want to reconstruct that. Say, okay, Na plus, it has a positive 1 charge. Well, by virtue of it being sodium, we know that sodium has 11 protons. How many electrons does it have? Well, 10 electrons. Because 10 of those electrons are going to cancel out 10 of those protons, but we're going to have 1 extra or 1 excess proton. Now, with that, so we've talked about the experiments that were used to kind of evolve this model of an atom, our subatomic particles, the mass of those, how we can put together our different numbers on our periodic table. There's one other number, or there's one number that we've looked at, and I kind of alluded to the other day, this number with the decimal place. Boron, 10.81, sulfur, 32.07, 35.45. Well, if we look at chlorine, 35.45. Chlorine has an atomic number of 17. So it has 17 protons. The other number on there is the sum of protons and neutrons. Don't fall into the trap of saying, oh, well, that means that I have 18.45 neutrons in an atom of chlorine. Because that's not correct. You can't have half a neutron. What this instead is showing you is the relative abundance of different isotopes. Because if we jog back for a second, here are 3 different isotopes of hydrogen. We have no neutrons, 1 neutron, and 2 neutrons. What is the abundance of these different isotopes? It's not, so if you were to go out and grab 1 hydrogen atom in the universe, it's not a 33, 33, 33, or an equal chance that you grab 1 of these 3. The most abundant hydrogen isotope is this one on the far left. These other 2 account for like 1/10%. So that's why we have this 1.008, because we're saying, well, this H3 accounts for 0.5%. This H2 accounts for 1%, and H1 accounts for 98.5%. So we calculate what is known as a weighted average of those different isotopes. We look at the abundance of them, give them a percentage, and do a calculation. So this is an explanation as to where that number is coming from. Sound good? Yes. Okay, so at this point in time, we're not doing any of those calculations, but I just want you to know where that number is coming from. And if you see on a quiz or a test something like this consists of 16 protons and 19.5 neutrons, know that that is not the correct answer. Deals? Great. Because your number of neutrons is always going to be a whole number. Okay. Electrons will determine the chemical properties of an atom. So models of electrons and atoms are based on experiments. So this right here is a really interesting experiment. What this experiment consists of is this black box over here is a spectral tube holder with a power supply. Essentially, this is like a glass chamber here, and somebody has sucked all of the air out of it, but so it's under a vacuum, and then they pump in hydrogen gas. So H2 is in there because H2 is one of our diatomic gases. So to the naked eye, that's what we see, this really cool magenta color. But then, has anyone ever seen the cover of Pink Floyd's Dark Side of the Moon, where light goes through a prism and it splits into all these different colors? So that visible light that you see, that prism splits it to all of the different colors that combine to make that white light. So that white light is every color. Okay, great. So when we look at this right here, we're like, oh, fantastic. That's a really cool, like purple magenta type of color. But if you subject this to a prism, that same prism that splits white light in every single color, what you see is actually there's only 3 colors. Those 3 colors combine, this red, light blue, and this navy, or this dark blue. Those are the 3 colors that come together to make this magenta. So what that means is that if you send an electric current through hydrogen gas, exclusively hydrogen gas, then that's going to produce an amount of energy that makes visible light with these 3 different colors. Now, similarly, if you get other gases and you make these same sort of spectral tubes where you remove all the gas and replace it with neon, nitrogen, helium, or hydrogen, you're going to get different colors. And why is that? Well, the reason for that is you're sending an electric current. You're basically, it's almost like you're taking that gas and you're shocking it. And that gas says, oh, here's the colors that make me up. It's very dramatic, we'll say. Neon is going to produce something like this. Nitrogen is going to produce different gases. So essentially what they're saying is all these gases make different colors whenever they are excited by an electric current. Similarly, if you were to get a sample of any one of these materials and burn them, which it's awfully fitting that yesterday was the 4th of July. So when you saw those spectacular different colors, you got to see any sort of fireworks. The reason that some were red and some were blue were because of the different materials that were in there in those incendiary or explosives that basically gave off those different colors. So it wasn't, that's why whenever you go watch fireworks, it's not like, cool, that looks like I'm burning a piece of paper. Instead, it's like, this is a massive explosion that gives off a bright, like pure orange. Well, that's probably a small amount of sodium in there. Oh, but what about this brilliant red? That would be because of lithium. So whenever you go to, let's see, when's the next time fireworks? Like around the 1st of the year. Next time you go and look at the fireworks stand, then every single thing in there, they're probably going to produce different colors. And that's because they have different chemical compositions of those explosives. And that's also going to contribute a little bit to, you might buy one of those. They always have silly names. I went to a fireworks stand with my son yesterday and they're all like, Bonzo Blaster 27,000, like a big number and a silly word is what they, why some of those are like, well, this massive thing is $13, and then this other small thing is $175. But of course, at a fireworks stand, as we all know, everything is like 99% off because that's how their marketing works, where they're like, oh, it's one-time sale, 99% off. Oh my gosh, you got to get it before it's all out, which is always silly because it's like, if I don't buy it, you guys can't sell it tomorrow. So you need me more than I need you. Anyway. Some of those cost differences are because some of these materials are different in price. Now, if we look at this, which metal might be in this party candle? We've got color options. Boron gives us a green. I don't see much green in there. So B's out. What about lithium? That's nice. This is pure lithium. Think about this as being, well, it's a wick with some of that metal in there. Maybe some lithium. What about barium? Green, copper, green. I think our best answer is probably that lithium there. Deal? Okay, so the idea, or like essentially, if we go back here to this spectral tube and the production of these 3 different colors, that is, so this shown here on the right is a line spectra. So these are the different visible colors that are produced. Now, the reason for this is that if we think about a hydrogen atom has, let's say that hydrogen atom has a mass of 1. It's got 1 proton. If that hydrogen atom is neutral, it's got 1 proton, 1 electron. Now, when you send an electric current through that, what's going to happen is that there is going to be about 1 electron. We've got millions upon billions of these hydrogens. You're going to send energy in, and that electron is, I always kind of visualize it as like, the electron is standing on a metal floor, and you sending the electric current through it is spontaneous, like very quickly heating up the floor. That electron is going to jump up. And whenever that electron jumps up, it's going to go to what is known as a higher energy. because it's depending on how quickly it senses it, it's going to jump way up. And then what it's going to do is it's going to be like, well, I went up, I eventually have to come down. So I'm going to come back down. Here what we see are 1, 2, 3 different pigments and 1, 2, 3 different lines representing where that electron was and the different what are known as energy levels that it went up to. When it goes up and then when it comes back down, so you put energy into it to get it to jump up, but then when it comes down, it releases energy. And that energy is released in the form of visible light. Now, this is all like, I always find this to be kind of, it seems very abstract. It's like, how do I wrap my mind around that? Whenever I think of energy, I think of, well, I put gas in my car. Boom, that makes sense because my car is doing this little explosion. Visible light, so something that is red, has a small amount of energy. Is it enough that I'm going to be able to fuel my car by shining a red light at my car? No, not at all. But it has a small amount of energy. So here, this hydrogen, when it gets shot up to this higher energy and then cools down, it's releasing visible light. So it's translating basically energy from an electric current into visible light. Does that make sense? Okay. So this electrical energy is converted into visible light energy. Now, what we see is there are a total of 3 different pigments, indicating that we have light energy or excitation energy. So we get electrons shot up to 3 different levels. Now, if we were to look at something that has, 10 different pigments, well, then that's electrons shot up to 10 different energy levels. And then they cool back down. It's like they jump up and then they cool down and release light in the process. So basically all of this was done to say, or it gets complicated and it's tricky, but essentially this right here, these 3 lines give a little bit of insight into what an atom looks like. Because this is almost like saying, okay, I'm going to send this electric current through hydrogen, which has 1 electron. And I happen to get 3 different pigments out of it, 3 different colors. Well, the idea is, well, that's because it goes to these 3 different electron levels. How could it go to 3 different levels? It's almost like, someone lives in a house, or we went to that atom's house, sent an electric current through it, and that hydrogen atom went up, and you learned that this house has 3 different levels. This is what we're learning here, okay? That's what this specific experiment tells us. Now, with more experimentation with different substances, you learn more information about what these different atoms look like. You say, okay, well, the atom that produces, 6 different colors. Well, that's a house that has 6 different levels. So we're piecing all this together and ultimately arriving at this theory known as the atomic orbital theory. And think about this as almost like someone took all of the information of the day, all of those different spectral line graphs, and they said, okay, well, every single atom, or every single, an atom of lithium, an atom of magnesium, an atom of calcium, or gold, or anything else, those atoms are made up of the same subatomic particles. It's different numbers of them and organizations of them, but they're made up of the same things. Now, we did these experiments where we learned how many floors, how many houses, or how many levels these different atoms' houses had. And we came up with a model that looks like this. And these are known as subshells. This is where we've gone from And typically, we're good up until we hit this slide. Everyone's like, okay, cool, I can follow that. Yeah, I gotcha. And then this slide is like, but interesting. We're going to walk through this deliberately. If we take a hydrogen atom, for instance, hydrogen has one proton, so it has one electron. If a hydrogen atom consists of one proton and one electron, can those two things that are opposite charged, well, they're going to be attracted to one another. Would everyone agree with that? Opposite charges, yeah, they're going to be kind of pulled in close. So that first electron of any atom is going to be close to the nucleus. And so if we visualize a hydrogen atom, you could kind of think about it with that super early theory of an atom and say, oh, it's just a sphere, it's just a ball. That ball in the center of it has a nucleus, and there's an electron on it, around it. Okay, so hydrogen, I think that's a pretty good one to follow. Now let's go to helium, He. Helium has two protons. Those two protons are at the exact center of a nucleus, or at the exact center of an atom in that nucleus. Now, helium, with an atomic number of two protons, it's also got two electrons. Okay, and so if we imagine that we're building a helium atom, we're going to put our nucleus in the exact center, then we'll put our first electron in. And that electron is like, oh, this is great. I see two protons in the nucleus. I have an opposite charge of them, so I'm going to go get close to those in the nucleus. Good. But that's not the complete story. Helium has two electrons. So when we put that second electron in, what's going to happen? Well, now all of a sudden, that second electron from that helium atom is going to say, well, I want to get close to the nucleus. And so other electron, go. Because they're going to have repulsed, the two electrons are going to repel one. So when one electron goes close to the nucleus, the other electron is going to be pushed away. Does everyone follow that? So that's like, this is taking place in constant motion. But we still have this sphere that we can pack those first two electrons in. Now, when we get to a third electron with lithium, that's where it gets a little bit hairier. We have lithium that has three protons and three electrons. Do we know where the protons are? Yep, they're going to be packed in the center and in the nucleus. What about our electrons? Well, we'll put one electron in and then another electron in. And those two are going to repel one another. Our third electron can't, and this is where we have to kind of adapt rules to the game. This S sphere, or this S red circle that I've drawn there, that can only hold two electrons. So where's our third one going to go? It can't go into that sphere, so it's got to go outside of it. Now, what we've got is it can go outside of that sphere, and that's where we have these kind of lobes, you could call them, where electrons can go. Okay, so our third electron with a lithium atom, one can go here. Does that make sense? So we'll stop there, but essentially these atomic orbitals provide a theoretical explanation for where all of the electrons in something like RF, root of 40, with 104 protons. If it has 104 protons, it's got 104 electrons. The very first two electrons are going to be in that S, that red circle. The third electron, fourth, and so on. they're going to, all of the electrons are going to try to get as close to the nucleus as possible, but they're all also kind of fighting one another off. Does that make sense? And this entire theory was put together because of spectral line graphs with hydrogen, and then with helium, then with sodium, and then any number of other substances where you see these different kind of, these different lines representing energy being released. So essentially, you might look at this and say, oh yeah, that's super cool. That's really pretty color. But what this is also telling you, when using the right tools, is it's giving you a little bit of insight into the structure of an atom, where the electrons are in a given atom. Okay. There we go. Now, this ultimately, what I want you to know about this right here is what these subshells are. They're known as the S, P, D, and F subshells. This is the periodic table with different kind of color scheme. These color schemes represent blocks. These blocks are known as S, P, D, and F block. Now, these S, P, D, and F blocks, these represent where the valence electrons, so the outermost electrons of an atom, which block they are in. So if we took something like, let's go with phosphorus. Phosphorus has the atomic symbol of P, has 15 protons, so it has 15 electrons. The very first 2 electrons in any atom of phosphorus are in this S subshell. But then the outermost electrons are going to end up in the P subshell. Okay, so what I want you to know is the very first 2, or the 2 very first electrons of any given atom, are in the S subshell. They are as close to the nucleus as they possibly can be. But then the outermost electrons, so I want you to know those extremes, the bookends there. The closest electrons are closest to the nucleus, and the farthest ones, which block of the periodic table are they? That's going to be valuable information. So if I were to ask you on an exam question, the valence electrons of zinc are in which subshell? Well, these first 2 columns on the far left correspond to the S. Columns on the right are the P block. In the middle, the D block, and then the lanthanides and actinides at the bottom constitute the F block. So if I asked about zinc, Zn, that would be, well, my valence electrons are in the D block. In addition to that, I want you to know these images well enough that if I showed you one of them, you'd be able to say, aha, that's the F, that's the P, that's the D. And just so you'll know, I will block out where it says S, F, P, or D on there. So know the structures or be able to identify those models. Okay, this table also tells us the number of valence electrons any given atom has. The outermost electrons determine the chemical properties of an atom. The last digit of the group number for main group elements. Your main group elements are the S and P blocks. So from everything on the far left-hand side, those first 2 columns, and then on the far right, columns 5, 6, 7, 8, 9, 10. Those are your main block elements. So if I were to ask you something like oxygen, how many valence electrons does it have? These numbers will be on here, they won't be highlighted, but you can look at that and say, okay, well, oxygen is in group number 6. So it has 6 valence electrons. So the way that I always kind of visualize this is I don't count up 13, 14, 15. I say 1, 2, 3, 4, 5, 6, and so on. So this, and the reason all of this is relevant or important is because this group in the middle and then the group at the bottom, they have very different chemical properties than everything else. So that's why we kind of omit those in this valence electron calculation. How many valence electrons are in carbon? Okay, so carbon, number 6. How many valence, not total electrons, but valence electrons? Well, we can look up here. 4. How many total electrons? 6. But valence electrons is 4. Now, classifying elements in the periodic table, we have group names. And we also look at things in terms of, are they metals or non-metals? This from number 3 to number 12. So from here to here, all of these elements that I'm putting a strange shaped box around, these are known as the transition metals. So they are metals, they have some kind of unique properties. The far left-hand side, group number 1. Those elements, we watched this video last time, these are what are known as alkali metals. Lithium, sodium, and potassium are examples of these alkali metals. Now, if we wanted to classify things as metals or non-metals, and we look at this depiction of the periodic table, there's a line that you can kind of draw, and that is right here. Everything to the left of that line, those are metals. Everything to the right of that are non-metals. Now, a great question that everyone always has is, but what about those elements on that line? And I'll ask you, like, to give an example. I mean, you have this periodic table, so it gives you the information, but Si, silicon. Silicon is in electrical outlets, it's in your computers, it's in everything. That has a, it's in every semiconductor. So when you think about what's a conductor aside from the person at the front of the orchestra? Something that conducts, right? So conducts heat, conducts electricity. If you had something, well, when you call something a semiconductor, does it conduct electricity? I think most people would hear the prefix semi and be like, yeah, kind of. And you're right, it kind of is. Silicon is a great example of what's known as a metalloid. That means that it has properties of a metal and properties of a non-metal. Now, as an example, if you, when metals are conducting electricity, what happens to them? They get hot. Sometimes they maybe even melt, okay? Now, typically, if you are using your phone, I'm gonna go with everyone has a smartphone. If you're using your phone, chances are it might get a little warm, but it's not gonna get super hot. It's not gonna get to a point where you're like, I cannot touch this, otherwise I'm gonna get a 3rd-degree burn on my hand. So it can conduct electricity without accumulating as much heat as something like steel or iron or anything like that. So it has the conducting ability at, say, metal, but it doesn't get as hot like a non-metal doesn't get super hot. So if you use that line as your dividing line, that's going to put you in a good place. Everything to the left of that is a metal, everything to the right is a non-metal. And then where that line is, metalloids. I think most people, what they're gonna do is they're just going to commit to memory B, S, I, G, E, A, S, S, B, T, E, P, O. And that'll do it. So we got into talk about a number of different a number of different substances. The organization of the periodic table, we dissected a lot of the periodic table. And learned about some different chemical properties. If any, I'm going to stop my recording. And we have our exam on Monday.